You ever stop and think about how a single thought, poof, just happens? Or how you decide to move your hand and it just moves? It's not magic. Not really. It's all about communication. We're talking about tiny, tiny electrical sparks firing between your brain cells. So how do these cells actually talk to each other to create, well, everything that makes you you? Come on, let's follow the journey of one single nerve impulse and find out. Okay, so let's meet the star of our show, the neuron. These are the messengers of your nervous system. And I mean everything you think, feel, or do. From a simple blink to composing a masterpiece, it all comes down to these incredible little cells passing notes to each other. So here's the big question, the one that frames our entire journey today. How in the world does an idea, a signal, travel that fast, over 200 miles an hour? It's not magic, I promise. It's this breathtakingly elegant electrochemical dance. And we're going to trace that signal's path from the very beginning to the very end. All right, first things first, we have to get properly introduced to our little messenger, because to really get how the message is sent, you got to know the basic layout of the messenger itself, right? Think of a neuron as being built for a relay race. The signal follows this very clear one-way path. It all starts at these branchy-looking things, the dendrites. They're the ones catching the message. The signal then zips over to the cell body, which is kind of like the command center. If the signal is strong enough, it gets fired down this long, long cable called the axon, all the way to the end, where the telodendria pass the baton to the next neuron in line. So what's a neuron up to when it's not sending a signal? You might think it's just chilling out, doing nothing. But that's not it at all. It's actually in a state of high alert, kind of like a charged-up battery, just waiting for the command to go. Now, this state of readiness has a fancy name, the resting membrane potential. It sounds super technical, right? But all it really means is that there's a difference in electrical charge between the inside of the neuron and the outside. And that difference is the potential energy that's going to power the whole show. And here is the magic number for a neuron that's just waiting, -70 millivolts. That's tiny, but it's so important. It just means the inside of the cell is about 70 millivolts more negative than the fluid on the outside. This negative charge is the starting line for every single nerve impulse. So how does the neuron keep that negative charge? Well, it's all about controlling traffic. The traffic of charged particles called ions. See, the cell's outer wall is kind of leaky, but it lets more positive potassium ions out than it lets positive sodium ions in. To keep this imbalance going, you've got the star of the show, the sodium-potassium pump. It's working constantly, like a little bouncer, pushing 3 positive sodium ions out for every 2 potassium ions it lets in. It's this hard work that keeps the neuron's battery charged and ready to fire. Okay, now for the main event. When a neuron decides it's time to send a signal, it doesn't whisper. It shouts. And this electrical shout is what we call the action potential. This is it, the nerve impulse, the spark that carries the message. Remember our resting state was at -70? Well, if the incoming signals are strong enough to nudge that charge up to this critical number, the threshold of excitation at -55 millivolts, then that's it. There is no turning back. It's the point of no return. And that brings us to something really, really important. Once that -55 millivolt threshold is crossed, the neuron fires completely. There's no such thing as a kinda or a weak action potential. I want you to think of it like a light switch. It's either all the way on or it's off. There is no dimmer. This whole thing happens in a flash, like a 4-act play. First up, depolarization. The sodium gates fly open, positive sodium ions flood into the cell, and the internal charge just skyrockets. Then, Act 2, repolarization. The sodium gates slam shut, and now the potassium gates open, letting positive potassium ions rush out to bring the charge back down. Next, a brief little moment called hyperpolarization. The potassium gates are a bit slow to close, so the charge actually dips even lower than its resting state for a second. And finally, the refractory period. This is just a quick reset, making sure the signal can only travel in one direction. So how does this signal travel so ridiculously fast? Well, the secret is insulation. A lot of axons are wrapped in this fatty layer called the myelin sheath, and this insulation has these tiny little gaps in it called the nodes of Ranvier. So the action potential doesn't have to happen at every single point on the axon. Instead, it literally jumps from one node to the next. And that process, called saltatory conduction, is what makes these signals so incredibly quick. So our electrical signal has raced down the axon at top speed. But now it faces a challenge. There's this tiny, tiny gap separating it from the next neuron. It's called the synapse. And the electrical signal, it can't jump across. So it has to change its form. Right here at the very end of the axon, the space is packed with these tiny bubbles called synaptic vesicles, and each one is filled with chemical messengers we call neurotransmitters. This is where the magic happens, where that electrical signal gets converted into a chemical one so it can cross the gap. This chemical handoff is it's a beautifully choreographed dance. When the action potential arrives, it opens these special channels for a key player, calcium. Calcium ions flood into the terminal, and that's the trigger. It tells the vesicles to merge with the cell wall and release their neurotransmitters into the gap. These chemicals then float across, they lock onto receptors on the next neuron, and boom, the message is delivered, converted right back into an electrical signal. But here's the thing. A single neuron isn't just listening to one other neuron. Nope. It's getting thousands of messages all the time from all over, some screaming fire and others whispering don't fire. And it has to add all this up and make a decision. You can think of it like a tiny committee taking a vote. And these votes come in two basic flavors. You've got your excitatory signals, which cause a little bit of depolarization. They push the neuron closer to that negative 55 millivolt threshold. They're the yes votes. Then you have the inhibitory signals, which do the exact opposite. They make the neuron even more negative, pushing it further away from the threshold. Those are the no votes. So the neuron has to do some quick math, adding up all these yeses and no votes. This process is called summation. It can add up signals from a bunch of different places at once, that's spatial summation, or it can add up a whole bunch of signals arriving really fast from just one source, that's temporal summation. And if the grand total of all those votes is enough to hit that negative 55 millivolt threshold, then and only then does it fire. So why does all this microscopic drama matter so much? Because this entire elaborate process, this is the fundamental way our brains change, adapt, and learn. This incredible ability to change is called synaptic plasticity. Basically, the connections between your neurons, those synapses, they aren't set in stone. Based on how often you use them, they can actually get stronger or weaker. This right here is the very essence of how we form memories and learn new things. And this happens in two main ways. When two neurons talk to each other a lot, their connection gets stronger, more efficient. We call that long-term potentiation, or LTP. It's the physical basis of that famous saying, neurons that fire together, wired together. But the opposite is also true. If a connection is barely ever used, it can weaken and eventually get pruned away. And that's called long-term depression, or LTD. And this brings us to a pretty amazing, mind-blowing takeaway. Learning isn't some abstract idea. Every single time you study for a test, or practice an instrument, or just make a new memory, you are physically rewiring your own brain. You're strengthening certain pathways, using the exact processes of action potentials and synaptic transmission we just walked through. So, from a single charged particle crossing a membrane to the vast, complex networks that create our consciousness, the journey of a nerve impulse is really the story of how we become who we are. And if learning is a physical act of creation happening inside your own head, it leaves us with one really powerful question. What new connection will you choose to build today?